Hey guys, today we're going to be looking at applying some problems with discontinuity and continuity. Last week at the end of the week you had two videos which introduced you to those concepts of identifying types of discontinuities and then also identifying continuous functions. So today we're going to be applying those to some problems on Delta Math. And I'm going to start by just doing a little bit of review over those types of discontinuities before we jump in. Also, if you maybe have forgotten it, if you watched it earlier in the prior week, maybe go back and rewatch those. They're not too long, so it'll be good to do that. All right, in this first section of Delta Math problems, we are supposed to identify jump discontinuities or removable discontinuities. So I want to start by just reviewing the different types of discontinuities. So the first one is called a removable discontinuity. A removable discontinuity is a function that has a little hole in it and then it keeps going. That hole may or may not be covered up by like another dot above or below it, but the idea is here, if we could just fill in that one little dot, then our function would become continuous. So we've sort of just removed one little piece of it. The second type was called a jump, also called a non-removable discontinuity. A jump discontinuity looks kind of like this. It goes, we might have a hole, and then it jumps up to here, and then it will keep going again. So in this one, we can't necessarily just fill in that hole and make it continuous because we got to jump up to the other function. So that's why it's called a jump discontinuity. The third one is called an infinite discontinuity. It's also non-removable, but is an infinite one. So an infinite discontinuity is generally the case when we have a vertical asymptote. Maybe our function goes like that and then goes down to negative infinity there. So it goes up to infinity or down to negative infinity, and there's no way we could theoretically connect these together because they're just going to keep going up forever. They could be opposite directions, it could be same directions, but basically the idea is we have a vertical asymptote there. So that's what gives us an infinite discontinuity. Definitely no way you could just put a dot and fill that thing in. And the last one was in one of the videos. They didn't have it in both of them because it's not used so much, but that was called an oscillating discontinuity. That's the case where you maybe have some like trigonometric function where it just kind of goes crazy and then it goes back out like that. Basically, you can't tell what it's approaching because it's just going, whack in there, and you can't tell what value it's approaching in either direction. So we call that an oscillating discontinuity. But these are the three main ones, the first three. All right, so we are supposed to identify a jump discontinuity in this problem. So let's just work our way through. It says on the interval -9 to 9, so it's basically this entire function here. And let's go identify the possibilities. So the first place, if we're just going to continue along here, well, there's a discontinuity right there because there's a hole. Now this is not a jump discontinuity though, because we could just fill this in with a dot. So that would be a removable discontinuity. So if we continue to go along this, here we get to another spot. This one is also a removable discontinuity because we could just put a dot there, fill it in, and keep going. Then we get to this one, if we put a dot there, we can't just keep going because we got to jump up to here. So that would be a jump discontinuity because we got to jump up to the other function. So at that spot, x equals 4, and then it just continues from there. So this point, x equals 4, would be a jump discontinuity. Type that in. And there we go. All right, next one, we're asked to identify where there is a removable discontinuity. So a removable, remember, is where you can just put a dot there and fill it in and it'll keep going. So let's start by tracing it. here. So we got a hole. I can just put it one dot there, and then I can keep going. So that is one. That's a removable one at -4. Continue here. Put a dot to try to fill it in. We got to jump up to that part, so that is not a removable discontinuity. Keep going here. You get to a hole. I can fill that in. It doesn't matter the fact that there's a dot up there. I can fill it in, so that is a removable one. Go around up here. Try to fill this in. I can fill it in, but then I got to jump up to here, so that is a jump discontinuity. Continue the rest there. So there's two spots there, -4 and 1. So to type this in, you're going to do -4, and then you hit this little plus sign here, and that gives you another place to answer. All right, let's maybe look at one more, another jump discontinuity. So let's just go a little bit faster here. So we go along here. This is a removable because I could fill it in. So keep going. Removable because I could fill it in. Keep going up. I got to jump to this curve. So that's going to be a jump discontinuity there at 0. I could fill that one in. This one, I got to jump to this one. So that would be another jump discontinuity. So it looks like at 0 and 7 are my two jump discontinuities. Okay, so hopefully you got the idea there. You're basically just going to be identifying those. I think there was, I could find. All right, here is an infinite discontinuity. So I did want to do one of those. All right, so an infinite discontinuity on this one is what we're looking for. As we go along here, that would be a jump to this one, right? Along here. Now notice this one, it doesn't have it written in there, but there is a vertical asymptote right there. This is going up to infinity. This is going up to infinity. So there's no way that we could just like put a dot. You'd think that, oh, I could just cross over infinity there. That is not the case. You can't just sort of fill in that infinity. So that is an infinite discontinuity there at x equals 3. And that's all there is to it. All right, we're going to look at a few other different types of problems. Let's start by erasing this stuff here. All right, so the next thing we're going to talk about is the definition of continuity, which was also in those videos. I'll go over that definition as well. So for something to be continuous, it has to really satisfy 3 conditions. 1, f of c must exist. That's saying the function has to be defined at that point. The second one is that the limit as x goes to c of f of x must exist. You might also, for one, it might say not must exist, but might be defined. Maybe it's a different, better word. So f of c must be defined. Limit must exist. Now, if the limit exists, that also implies that the limit as x goes to c from the left equals the limit as x goes to c from the right, meaning the right and the left limits agree, because if a limit exists, we know that the left and the right match. And the third condition is that f of c, the function value, must equal the limit. So the function must be defined, the limit must exist, and that point where it's defined must be the same as the limit. So those 3 conditions. Really, it just boils down to this. Those other 2 are just sort of precursors to get you to that point, because if f of c is not defined, well, then it can't equal the limit. And if the limit doesn't exist, then it can't equal f of c. So really, 3 is the main thing you need to be concerned about, but those other 2 sort of build up to this one. All right, so let's see if we can answer the question. We got a lot of boxes to fill in, but that's good because it helps reinforce this definition. It says we're supposed to use the definition of continuity, which we've got here, to determine whether the function below is continuous at x equals -5. So first thing let's do is let's just go to -5 and see if we think it is continuous. So -5 is right here. And it's pretty obvious that is continuous there at -5, right? Nothing happening, it's just a smooth curve. So let's see if we can fill in all of the blanks. All right, so the first one asks for the limit from the left. That's the left-hand limit. So that means if you're going to trace this function in from the negative direction, it's going to go in that way. What y value is it approaching? Well, the y value down there is -6. So -6 from the left. From the right, it's going to be the same. Also approaching -6. Which means that the limit has to exist because those are the same, and it also has to be equal to -6. So those are good because they reinforce the second point here. Left and the right are the same and they exist. Furthermore, it can be seen that f of -5, so that's what we're talking about, that f of c must exist. That does exist because it's just a smooth curve there. It is also -6. Therefore, it can be stated that the function is continuous at x equals 5 because the limit as x equals -5 is equal to f of -5. So that's kind of the final conclusion there of our definition of continuity. All right, so let's go ahead and submit that. Like I said, this is really good because it reinforces that definition, which you will definitely be quizzed on the AP exam. All right, next one. Should be a little bit more interesting one here. We'll have some different answers. So we're supposed to determine if this is continuous at x equals -6. So let's first just look at that. Here's -6 here. Well, it's pretty obvious that it is not continuous, right? We've got a jump discontinuity going on there. So we know that's going to be not continuous, but let's see if we can still prove why. On the AP test, you'll be asked, like, why is this not continuous? And you'd have to give a good justification of why using this definition of continuity. So let's first look at the left-hand limit. That's what we're supposed to find there. So the left-hand limit would be coming down the curve that way. As we approach from the left, we get the y value of -3. So that's what we're going to type in there. It's not enough to just know it's not continuous. We need to prove why. So that's what we're doing. The right-hand limit is going to be just a little short spot here. As we're moving in from the right towards -6, our y value is down there at -6. So that's going to be our right-hand limit, which means that the limit does not exist because the left and the right do not match. Furthermore, it can be seen that f of -6, so we need to figure out if f of -6 exists. Turns out it does not, because at -6, this is open, this is open. There's no filled in dot anywhere, so it doesn't even exist there. So we're just going to hit, I think, D and E. I'm not sure which one, actually. I think we'll go with D and E. Therefore, it can be stated that the function f of x is not continuous or discontinuous at x equals -6 because we got to choose one of these three. The limit, that does not exist. That is true. Let's see. All right, that's got to be it. All right, yeah, there's actually multiple reasons why. It fails both of those. The limit does not exist and the function's not defined. So I think that was the only one that's see in the drop-down box. And there we go. All right, we can maybe look at one more. Looks like this is maybe the third reason here. All right, so we're supposed to determine if it is continuous at x equals 1. Let's first make the determination if it is. Well, it is not continuous there at x equals 1. We've got a removable discontinuity, which means it's not continuous. But let's go through and find these limits. So as we approach from the left, heading in this way, the y value is 0. As we approach from the right, the y value is also 0. Right as we come in here, the y value approaching is 0. So the limit does exist because the left and the right are both 0. so the overall limit is 0. Furthermore, it can be seen that f of 1, so the actual function value, it does exist, right? There's a dot right there. However, it's at -1. So the first two conditions actually hold in this case. The limit exists, f of c is -1. However, it is discontinuous or not continuous at x equals 1 because the limit exists but does not equal f of 1. That would be our answer there. All right. So I really like this activity in particular. It really trains you how to use this definition of a limit. All right, well, let's go on to some more here. Lots of practice. All right, now we get to look at piecewise functions. You often see continuity problems with piecewise functions as well. We're still going to use this definition of a limit in order to solve these. And how we're going to do that is we still have to make sure that the limit and f of c are equal. I'm not going to write out the whole thing, but that's the main thing we're going to check. So how we're going to do this is we're first going to find the limit and then find the function value. To find the limit, we have to do both the left and the right. So we're supposed to determine if it's continuous at x equals 3. So that's going to be our c value is 3, which means we need a left-hand limit at 3. And then we're going to need a right-hand limit at 3. To do this, we need to figure out which equation inside the piecewise function we're going to use. So for the first one approaching from the negative, or you could think of it as like the less than direction, we're going to use this one, right? Because value is less than 3, approaching from the left. We're going to plug 3 into this function. So we're just going to do 6 minus 3 squared. That's going to be 6 minus 9, which is -3. Okay, now the right-hand limit is going to be approaching from numbers bigger than 3, so I'm actually going to use this function. So it's still going to be 6 minus 3 times 3, 6 minus 9, which is still -3. All right, so our first thing to note is that the limit actually does exist, right? We can now say that the overall limit as x goes to 3 does equal 3. So that's a good check mark for first condition. Second condition, or depending on what order you do it, f of c must be defined. So f of c just means f of 3 in this case, because c equals 3. So we're going to plug it in where the equals part of it is. It's going to be that equation because that has the or equal to part under it. So we're going to do 6 minus 3 squared, and we get 6 minus 9, which is -3. That should be negative. So that is defined. And then the last check is to make sure these are the same, that f of 3 equals limit as x goes to 3 of f of x. Is that true? Yes, it's true. So that means this is continuous at this point. So you got to just run through the conditions there of continuity. Okay, let's try this one. Erase this real quick. All right, so very similar here. You're going to want to start and find the left and the right limit first. And then we're going to see if that's equal to the function value. All right, so let's start with the limit as x goes to -2 from the left, and the limit as x goes to -2 from the right. Remember, c is -2 in this case. So we need to choose which function. For the left side, we're going to choose this one, right? Because those are numbers less than -2. So 13 minus 2 times -2. That's going to end up being 17. And for the right, we're going to plug it into the top one because that number's bigger. So 9 plus 2 times -2. squared. So this becomes 9 plus 8. So that is 17 again. So that's good. That means our limit exists. The next case is to determine what the function value is, f of -2. And some of the problems on the AP test, you'll generally see like a third part of this, and it might be, maybe it would say like 5, and then it would just say specifically x equals -2, and then maybe you wouldn't see this one down here. Those are a little more interesting ones where you have 3 conditions, and in that case, you'll see more where the function is discontinuous. This one, that's not the case though. You're just going to plug it into the same one as the other one. So not as interesting, because we're going to plug it into the same function, and we'll know what the result is. Again, we plug it in here because it has the little line underneath of it. 13 minus 2 times -2, which is 17. So that exists, and it is, as we can see, the same as the other one. All right, so that is continuous. All right. Again, I don't see any ones that are extremely different here. Let me see. All right, let's see if this one is a not equal to. I think we might. Okay, actually, this one will be good. Now this one, if you're smart, or if you're just observant, shouldn't say smart, if you're observant, you'll notice something from the outset that tells you what the answer is. So we know our 3 conditions are the limit must exist, the function must be defined, and then the limit must equal the function value. However, if you look at our function here, this has an x greater than 2, has an x less than 2, but it does not have an x equals 2, whatever that is. It doesn't have a line under one of those. So actually, I can tell you from the outset here, f of 2 is not defined. Therefore, we know that this function is going to be discontinuous at 2 because it doesn't even give us a value for 2. If you wanted to, you could just, for the heck of it, find the limit values of this, but it would be good practice, I suppose. So if we went 2 from the left, we would plug it into the bottom function. That would be 9 minus 4, which would be 5. And the limit as x goes to 2 from the right would be 19 minus, looks like 16. Yeah, so that would be 3. So these are actually not the same either. So the limit does not exist, so it fails that condition. The function is not defined, so it fails that one. And obviously they're not equal. The limit does not equal the function. So sometimes you'll see on the AP test where it'll be like 1 is true, 1 and 2 are true, 1, 2, and 3 are true. Those are the worst questions because oftentimes you can figure out one of them is not true, but determining if more than one is not true is the hardest part. So this one might be the case where it's a multiple choice question and you have to determine why it's discontinuous. Well, all 3 reasons it would fail because the limit does not exist, the function is not defined, and the limit does not equal the function value. So this would fail all 3. So you would need to select like 1, 2, and 3 for why this is discontinuous. All right, and let's look at our last problem type. Finding the k value. These I have seen on the AP test pretty regularly as well. Generally, maybe a little bit more complicated piecewise function. These are maybe just slightly too easy, but the concept of these is really good. All right, so we need to find a k value that makes this function continuous. K is just a representative of a constant. Could be c. K is used a lot, I think, because it's a little easier to see than a c. So we need to find the k that would make this continuous. Now, based on the previous problems we just had, we know that if a function is continuous, the left and the right limits must agree, right? So that's what we have to ensure in this one, is that the limit as x goes to 2 from the left equals the limit as x goes to 2 from the right. First off, let's make sure that happens. So if that's going to happen, well, if I'm going to take the limit as x goes to 2 from the left, I'm going to be plugging it into the bottom one because that's less than 2 values. So I'm going to be plugging my 2 in. It's going to be k times 2 minus 10. Now I know this has to equal the limit from the right, so this thing must equal limit as x goes to 2 from the right, which from the right I'm going to use my top function, and that would be k times 2 squared. So in order for this thing to be continuous, if the left is going to equal the right, I need these two things to be equal. So I'm going to drop the limit part of those and just do, this is k times 2, or 2k, minus 10, must equal 2 squared is 4, so it would be 4k. So these two must agree if this thing is going to exist. So then I'm simply just going to solve for k. So minus 2k, minus 2k. Negative 10 is 2k. Divide by 2. So k is negative 5. So that makes these values equal. In other words, this function would be written as negative 5x squared and negative 5x minus 10. That would make this function continuous. You could also check by plugging in for f of c, it would just go in the top one, and that would become negative 20. So the right value would be negative 20. F of c would be negative 20 based on the top function. The bottom function, if you just wanted to double check, if I plugged 2 into that, it would be negative 10 minus 10, so that would be negative 20 also. So that's a good check to do before you submit your answer. So my k value should be negative 5. Let's do another one of these. Oh, this looks like a fun one. Okay. We got a fraction here. All right, so the setup for all of these is going to be the same. Again, a reminder that there's that help video on these. So if you don't like my explanation or you're not quite getting it, feel free to tune into that help video. I haven't watched it for all these, but some of them I have watched, and they give a, might give a slightly different explanation. So it's always helpful to watch those if you need it. All right, so we need to make this thing continuous. Now, this is a little bit different scenario because our two conditions are x equals this or x does not equal this. So basically, we're going to use this function for the not equal part for both the limit as x goes to negative 3 from the left, and we're going to use it for the limit as x goes to negative 3 from the right. So since we're going to use that function for both of them, right, because this is whether you're going from left or right, you're going to use this function, we know that we're going to get the same value, right, because we plug it in. If we plug it in from the left, we're going to plug in the same function. Plug it in the right, we're going to get the same function. So the limit will definitely exist on this thing. And let's go ahead and figure out what that is. So the limit as x goes to negative 3, we're just going to plug it into our function, negative 3 squared plus 2 times negative 3 minus 3 over negative 3 squared minus negative 3 minus 12. So we get 9 on top minus 6 minus 3. On the bottom we get 9. That becomes plus 3 minus 12. All right. Let's go ahead and evaluate this. We might run into a little bit of a problem here. Let's see, we get negative 6 over 0. Yeah, as our answer. Okay. So it turns out this doesn't have any places where the limit exists. right? Because we actually got an undefined answer for this on the surface here. The other thing we might actually want to check on this is to make sure that we can't factor something out on this and cancel. Because remember, we can't just say a limit doesn't exist if we get 0 on the bottom. That's what we did on that first time we did that assignment, and I made you go back and we did a lot more problems to practice this scenario some more. So don't assume this is just D&E based off of this, because it looks like we might be able to factor and cancel something out of that. So let's see if we can do that. On the top, that would factor into x plus 3, x minus 1. And the bottom, x plus 3 and x minus 4. Well, looks good. We did end up getting something to cancel, so that's very good. So now let's go ahead and try to plug in that -3 again. Turns out there is a place that exists. We're just going to substitute that -3 into here. And we get -4 over -7, it looks like, which would be a positive 4/7. All right, so that is our limit, 4/7. Probably would never have guessed that. All right, that's our limit. As x goes to -3. All right, so now if the limit equals this, we know this thing must equal f of -3, right? In order for this to be continuous. So now we can look at this other function. Turns out it's not really a function at all. It's just a constant. We know that it has to equal f of -3. Well, if it's just a constant, then that constant turns out has to just be 4/7 because we got the limit is 4/7. So we know that thing, k, just has to be 4/7 because that has to equal k, right? This limit must equal k. Now, if it was like 2k or something, then we would divide by 2. But in this case, it's just k. So we know that that function value must also equal 4/7 if this function will be continuous. All right, so that was kind of a crazy problem. Didn't see it go on there at the outset, but you can see that is how they solved it as well. They always give you the solutions here, factored out, canceled, plugged it in. So this one actually, if you were to look at the graph, has a vertical asymptote there. I would like you not to look at the graphs because this would be a non-calculator question, but you can see here they looked at the graph as well to make it work. And 4/7 is the correct answer. All right, I think we got maybe time for one more here, just to make sure you got the right idea. A lot of erasing here. All right. This one shouldn't take nearly as long. Okay, so on this one, again, we want to make it continuous. Find the k value that makes it continuous. So we need the left and the right to be equal, which is going to be the case in this one. So the limit as x goes to 6 because that's the value that's written there. From the left, first of all, well, if we're going to do it from the left, we're going to use this bottom function, right? It's less than. So that's going to be k times 6 minus 5. In other words, 6k minus 5. And that has got to equal the limit from the right. Hopefully you're getting tired of this definition of continuity at this point because that means it's getting stuck in your head. All right, so we just plugged in 6 there for the x. We need these two things to be equal. So this should equal 6 times 12 is 72 minus 29. So 6k minus 5 equals 43. Add the 5 over. 6k is 48. So divide by 6, and k equals 8. that will make it continuous. We shouldn't have to worry about the f of c value in this one. It should be good to go because it does have the or equal to underneath of there. So that would be just plugging it into the same function. If you did want to double check, 12x minus 29 equals 8x minus 5. You could just plug those in there, plug in 6 into each one. We would get 72 minus 29. 48 minus 5 should end up being equal. This one is 43, and that one's 43 also. So quick check there. So our k value of 8 must be correct. Computer, there we go. All right, so that is it, guys. I know there's a lot going on there, a lot of different types of continuity questions. This is definitely a concept that's on the AP exam. This is a lot of different ways to practice it. Reach out to me if you are getting stuck on any of these. Remember the help videos as well, and best of luck completing these.